In this lecture video, we're going to look at what's called a confirmatory factor analysis, or CFA model. This is a particular type of structural equation model. Here's an outline of what we'll be looking at in this video. We'll first briefly describe the example to provide some context for what we'll be doing. We'll then specify the CFA model as a system of statistical equations. Finally, we'll specify the CFA model graphically by creating a path diagram for it. So let's jump in. Let's first describe the example. Consider a confirmatory factor analysis to determine the relationships between a person's ability, their achievement motivation, and their aspiration. These are considered to be latent constructs, and you'll remember that latent constructs are unobservable characteristics. Latent constructs are also called factors. Now, it's proposed that three manifest variables are indicators of ability, and you'll recall that manifest variables are variables that are observable and therefore measurable. And so we have three observable measurable variables that are indicators of ability, three manifest variables that are indicators of achievement motivation, and then two manifest variables which are indicators of aspiration. Now, to construct the confirmatory factor analysis model, we'll go through the 5 steps. Step 1 is to identify all latent constructs or factors as well as the manifest variables comprising the structural equation model. In step 2, we'll specify an equation for each one-way explanatory predictive relationship in the SEM. In step 3, we'll specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. In step 4, we'll identify all model parameters to be estimated. And then in step 5, we'll construct a path diagram for the confirmatory factor analysis SEM. So let's look at step 1. Identify all latent constructs or factors and the manifest variables comprising the SEM. So as stated in the description of the example, we have three latent constructs in this example. F1 will be used to denote the ability latent construct. F2 represents the latent construct achievement motivation, and F3 will be used to denote the latent construct aspiration. There are 8 manifest variables in the model. V1 is a general ability score. V2 is GPA in the last year of high school. And V3 is the GPA in the first year of college. V4, V5, and V6 represent measurable achievement motivation scores. V7 is a general educational aspiration score. And then finally, V8 is a general vocational aspiration score. The manifest or observable variables that are indicators of the latent construct ability, or F1, are the three manifest variables V1, V2, and V3. V1 being general ability score, V2 the GPA in the last year of high school, and V3 the GPA in the first year of college. The manifest variables that are indicators of the latent construct achievement motivation, or F2, are the three achievement motivation scores, V4, V5, and V6. And finally, the manifest variables that are indicators of the latent construct aspiration, or F3, are V7, the general educational aspiration score, and V8, the general vocational aspiration score. Next, we'll look at step 2, where we specify an equation for each one-way explanatory predictive relationship in the SEM. So here we have equations that involve the factor F1, the ability latent construct. And so we have V1, which is the general ability score, being equal to lambda 1 times the latent construct F1 plus a random error term E1. And so you can see here that this is a regression type of relationship, with lambda 1 being the slope coefficient multiplied against the latent characteristic or latent construct F1. The next equation is V2, which is the GPA in the last year of high school, being related to F1, the ability latent construct, through the equation lambda 2 times F1 plus its own error term E2. And then finally, V3, the GPA in the first year of college, is related to the ability construct through the equation lambda 3 times F1 plus E3, which is its own error term. The equations involving the factor achievement motivation, or F2, to its indicators are as follows. So V4, again, represents achievement motivation score 1, and that's related to F2 through the equation lambda 4 times F2 plus E4. V5, which is achievement motivation score 2, is related to F2 through the equation lambda 5 times F2 plus E5. And then finally, V6, the achievement motivation score 3, is related to the achievement motivation factor F2 through the equation lambda 6 times F2 plus E6. Finally, the equations involving the factor aspiration, or F3, are as follows. So V7, which is the general educational aspiration score, is related to the aspiration factor F3 through the equation lambda 7 times F3 plus E7. And V8, the general vocational aspiration score, is related to the aspiration construct through the equation lambda 8 times F3 plus E8. And so here we have all of these regression type of equations on one slide. Notice that we have different slope coefficients in each equation. We have different lambdas for each equation. So we're allowing for those slope coefficients to be different across the equations. Note also that we have separate error terms for each equation. And so the various regression type models have their own error terms. Now note that the SEM includes equations relating the factors to the manifest variables they impact. Each of these equations is regression-like. Note, however, that there are some differences between these equations and the regression equations we have seen in other courses. In particular, note that in each of these equations, everything on the right-hand side of each equation is either an unknown constant or an unobservable random variable, either a factor or an error term. Okay, we recall the structure of these equations. V sub I, which is a manifest variable, being equal to lambda sub I times an F sub j plus E sub I. This is different from a typical fixed effects regression equation, which has one or more observable explanatory variables on the right-hand side. So think about that for a minute. The right-hand side of each of these regression equations is completely unobservable. In step 3, we're going to specify notation and or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. And so you'll recall that a structural equation model, as part of its specification, includes equations describing assumed relationships between error terms, between factors, and between factors and error terms. And we have listed these for this particular model on this slide. And so the first bullet point shows that we are assuming that the various error terms are uncorrelated. They are pairwise uncorrelated. Now, the second bullet point is specifying notation for the variances of the individual error terms. We're not setting them equal to a particular value. We are just defining notation for those variances. And so the variance of the ith error term is going to be denoted in this example by theta sub I going from 1 to 8. In the third bullet point, you'll see that we are assuming in this model, and therefore imposing the constraint, that the factors and the error terms are pairwise uncorrelated. They have a covariance or correlation of 0. In the fourth bullet point, we are defining notation for the variances of the covariances of the factors. And so we are allowing the factors to be correlated, to have non-zero correlation. And then finally, in the fifth bullet point, you'll see that we are specifying that the variances of the various factors are each equal to 1 in this model. Now, the reason for doing this will be discussed in a subsequent lecture video, but we just want to point out that this is a constraint that's going to be imposed on the model fitting process. Step 4 is to identify all model parameters that will need to be estimated. So first, we have a number of what are called loadings, the lambda sub i's. These are the coefficients multiplied against the latent constructs in those regression style equations. And so we have loadings lambda 1 through lambda 8. And so therefore we have 8 loadings, 8 parameters that will need to be estimated for that part of the model. In addition, we have variances of the error terms. The variance of E sub I, you'll recall, is denoted by theta sub I. And so we have 8 parameters that need to be estimated there. And then finally, we have covariances between the factors. And so cap theta sub 1, 2 is the notation for the covariance of F1 and F2. Cap theta 1, 3 is the notation for the covariance of factor 1 and factor 3. And then finally, cap theta 2, 3 is the notation that represents the covariance between factor F2 and factor F3. And so we have 3 parameters there. And so you can see that there are 19 model parameters that will need to be estimated in order to fit this structural equation model. Now, a couple of questions I want to pose and have you think about. What are necessary conditions for these parameters to be identified? In addition, what conditions will lead to the estimators being reliable? These are important questions because, number one, we want to be able to estimate the parameters in the model. We want to be able to fit the model. And on top of that, we want the parameter estimators to be reliable. We want them to have as small a variance as possible. And so be thinking about this. What are necessary conditions for these parameters to be identifiable, and what conditions will lead to estimators that we can be confident in, that will lead to estimators that are reliable? Step 5 in our process is to construct a path diagram for the confirmatory factor analysis structural equation model. Now, you will recall that ovals or circles are used to represent latent variables in a path diagram. And there are going to be 3 ovals in this particular path diagram for this particular confirmatory factor analysis. We use rectangles or squares to represent manifest variables in a path diagram, and there will be 8 of those in this model. Note also that there are 8 error terms in this particular model, which will be represented in the diagram by their respective letters, so E1 through E8. In addition, one-sided arrows are used to represent relationships that are one-way, directional, predictive, in other words, the regression type of relationships. Two-sided arrows are used to represent relationships that are two-way or correlative or mutually impacting. And then finally, parameters to be estimated are indicated in a path diagram by using asterisks. So here is the path diagram for this confirmatory factor analysis model. Let's look at the various components. First, let's look at the latent constructs, the factors in this model. You'll recall that the latent constructs or factors are the unobservable characteristics or unobservable constructs in the model. And so we have F1, which is ability, F2, which is achievement motivation, and F3, which is aspiration. So those are the three latent constructs in this model, and they are represented by ellipses, ovals, or circles, as we see here. Next, let's look at the manifest variables in this model. You'll recall that manifest variables are observable and therefore measurable, and they are denoted using squares or rectangles in a path diagram. And so the manifest variables, you can see, are outlined in this red box. We have 8 of them, V1 through V8. Again, V1 being the general ability score, V2 being the GPA in the last year of high school, and V3 being the GPA in the first year of college. Now notice that these 3 manifest variables, which are response type variables in the equations relating them to their factor, they have incoming arrows that come from F1. And so this is showing us visually or graphically that factor 1, which represents the ability construct, is impacting V1, V2, and V3 directly. Ability is impacting general ability score, V1, GPA in the last year of high school, or V2, and V3, GPA in the first year of college. Because we don't have any one-way arrows from F1 to any of the other manifest variables, F1 is not impacting V4 through V8 in a direct fashion. Note also that V4, V5, and V6, which are the 3 achievement motivation scores, have one-way arrows coming into each of them from F2, which is the achievement motivation construct, but there are no one-way arrows coming from F2 to either V1, V2, V3, or V7 or V8. And so the achievement motivation construct is impacting only, according to the theory shown by this model, to impact V4, V5, and V6. And then finally, F3, the aspiration construct, has one-way arrows emanating from it to V7 and V8. And so F3, or aspiration, is directly impacting, according to this model, the general educational aspiration score, or V7, and the general vocational aspiration score, or V8. F3 is not impacting, directly at least, V1 through V6. However, notice we have two-way arrows between each pair of the factors. So we have a two-way arrow between F1 and F2, a two-way arrow between F1 and F3, and a two-way arrow between F2 and F3. And so what this would allow is for F1 to indirectly impact the other manifest variables, V4 through V8, by its impact on its correlative relationship with F2 and F3. And likewise, we can see that F2 could impact the other variables, V1 through V3 and V7 through V8, by its correlative impact on F1 and F3 respectively, and so on. Next, let's look at the error terms in this model. And so E1 through E8 are the error terms in the model. These correspond to the error terms associated with each of the response variables, V1 through V8. And in general, there's going to be an error term associated with each response variable in a structural equation model. Next, let's identify the endogenous variables in the model. And so you'll recall that an endogenous variable is a variable that shows up as a response variable in one or more of the equations in the structural equation model. And so for this particular model, this confirmatory factor analysis model, the endogenous variables are the manifest variables V1 through V8. These are the only variables in this confirmatory factor analysis model that participate in the model as response variables in this system. And then finally, let's identify the exogenous variables in the model. You'll recall that a variable is an exogenous variable if and only if it never participates in the system as a response variable. And so we have F1, F2, and F3, the three factors. These three constructs never participate in this model as response variables, and so they are exogenous variables. In addition, the error terms, E1 through E8, are never a response variable in this system, and so they are exogenous variables as well. Now note that exogenous variables are very easy to identify in a path diagram because exogenous variables are those variables or those constructs in the path diagram that have no incoming one-way arrows. And so you'll see here that F1, F2, and F3 do not have any incoming one-way arrows, nor do E1 through E8. So they are the exogenous variables in this model. On the other hand, V1 through V8 each has at least one-way arrow coming into it. And so those are the endogenous variables. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.